Welcome to today's lesson. I'm Ziamasaka Kiriandens, and so today I'm going to take you through a lesson on refraction. So we go straight to the lesson for today. Well, refraction is actually the bending. It's the bending of light when it passes from one medium to another medium, or one material to another material. So there should be actually different materials here where light is actually passing through, and therefore it will bend. And so there are certain facts that we need to actually explain here or to consider when we are talking about refraction of light, in particular at a preliminary level. We know that actually a ray of light is bent towards the normal. It's going to bend towards the normal when it enters an optically actually denser medium. So a material can also be known as a medium if it enters at an angle. This is very important, as we'll see in future, at a particular angle. So it will bend towards actually the norm. What this means is that this is less dense, since this is air, and this is actually denser, since this is glass. So we note that if this did not bend, it would have gone straight through using that path straight. But because it is speed, the ray of light, actually speed reduced when it entered a denser material, and therefore it is actually bent towards the normal, and this is the angle of refraction. Okay, so that's what that means. Then a ray of light actually traveling, a ray of light actually is bent towards away from the normal when it is actually it enters an optically less dense material. What that means is that this is denser, glass, again, this is less dense. What it means that this should have taken that path, but because it has entered a less dense material from a denser material, so it is actually refracted away from the normal. And so we need also to describe here that actually this ray which is entering is known as the incident ray, and the angle between the normal, this is the normal, which you draw actually at 90 degrees with the edge where you are entering the new media. And so this is known as the angle of refraction, angle of incidence. It's known as the angle of when it actually before it is refracted is known as the angle of incidence. So when it is refracted or it bends, it forms this ray which is refracted, which is actually refracted ray, and the angle here is known as the angle of refraction. This is known as the angle of refraction. And this one is known as the emergent. the emergent lay. And so, what it means, as we are indicating here, we said actually the lay is going to be actually refracted away from the norm when it moves from a denser material to a less dense material or medium. And then the second part we consider is that a ray entering from a parallel-sided block is parallel actually to the ray entering. So the one which is emerging will always be parallel to the one which is entering. What it means is that this is the emerging ray. So this emerging ray, this ray which is emerging will be parallel to the one entering. If you notice here, they are actually parallel. Okay. And then a ray traveling along the norm will never be actually be bent. It will continue with the course of direction without bending if actually it is actually striking that edge of the other at 90 degrees. So in other words, what it means is that here, if you have a ray, it is striking at 90 degrees, it will not be refracted and it will come out from there at 90 degrees. So that's what it means actually. And the light is refracted because its speed changes as it enters or leaves another medium. So the bending is as a result of actually a change of speed because of the different densities. So the speed in a less dense material, it will be higher. And when it enters a denser material, the speed actually reduces. And so now at times we're asked to actually demonstrate through an experiment how actually we can demonstrate diffraction of light. And this is what we're going to do. The aim is actually to trace the cause of ray of light as it passes through actually the rectangular glass slab. And the materials we require are actually the rectangular glass slab, the drawing pins, the sheet of paper, pens, a pencil, or we might require also a ruler here. Okay, so these are the materials and these are called apparatus because these are the actually equipment which will help us actually, or materials which are going to help us actually demonstrate this experiment. Okay, and so the procedure is basically, first thing is to fix actually a sheet of paper on a drawing board with pins. In other words, what it means is that you fix maybe a pin there on a board, another pin there, another pin there, and another pin there. And this is on actually a board, which we said actually you fix on a board, a drawing board. So number two is that you place the rectangular block at the middle of the paper, where we have placed this paper here. Remember, we place the paper and then you put pins. And so you place now the rectangular block in the middle, the way we have done here. You place it in the middle of this paper, place there. And you draw around there, you trace it, you draw the pencil around it, making its shape as when you place it in the middle. And then, and you label actually these sides A, B, C, D, as we have done here. So you're going to label, this one is A, this is B, this is C, and this one is D. And then, actually, you remove the rectangular glass block, and then you fix the two pins. That is actually pin 1 and pin 2 at an angle. Draw a line 1, 2, making an angle of 30 degrees. So in other words, what it means that you can get a point between 1, this is 1, and then this is 2. You draw a normal here. A normal is actually an arbitrary line which is at 90 degrees to the edge where actually this ray of light is entering another medium. 90. So you draw here, right? And then you draw a line from 1 to this point to meet this point, just where this one actually enters. And so what you do now, you fix the pins. Pin 1 along 1 and 2, and pin 2. Fix them to make an angle. So this angle is known as the angle of incidence. It's actually the angle between the normal and the incident ray. So this one is known as the incident ray. Incident ray. Okay, so you fix a pin along the incident ray here. Along the incident ray, you fix a pin there, another pin there. And then you bring back the slab, place it. Okay, when you place the slab, then I've already indicated that you fix actually pin 1 and pin 2 along 1 and 2, and then you look through actually the images of pin 1. Look for the image of pin 1 and pin 2 on the side, on the opposite side of CD, and you fix then the pin 3 and pin 4 so that actually they appear in the same line with the images of pin 1 and pin 2. In other words, what it means is that once you bring back the rectangular block, you place it there, while these pins are on the other side, they are pin 1 and pin 2, and you come here where I've written an I, you check through for pin 1 and 2, see their images, and when they are in line, you place pin actually 3 and pin 4, such that when you check through here, they are in the same line. Pin 1 and pin 2 and pin 3 and pin 4, they are in the same line. And once you do that, you can draw now a line from 3 through pin, from point 3 here through pin 3 and pin 4. And this is what is known as the emergent ray. Emergent ray. And then you can join, you can make a normal here, another normal. At 3, you make a normal, such that this one is at 90 degrees. The normal is 90 degrees to this edge. And then you join a line from 2 to 3, and this forms what is known as the refracted ray. Refracted. This will form actually what is known as refracted ray. And then the angle between the normal and the refracted ray is known as the angle of refraction. Angle of refraction. This is the angle between the normal and refracted ray. And so we have already explained all this. So in other words, you measure the angle of incidence and the angle of actually refraction. And all these should be measured from actually the normal, which we have already done. We can as well draw a perpendicular from 3 to T, which forms actually what is known as the lateral displacement. So in other words, imagine this ray did not bend. We draw a line along that as if it is not bent. And then from the point where actually it at 3, where actually it emerges, it comes out of the prism, you draw this line, and this is known as the lateral actually displacement. So the lateral displacement will depend on the density of this material. If the material becomes denser, what it means that the lateral displacement will be longer, because the refracted ray will go actually more towards the normal, to be somewhere there towards the normal, and therefore this distance will be greater. If this one becomes less dense, it means that the refraction will be actually somewhere there. It means that also the lateral displacement will be shorter. Okay, so that's what actually that means. And so from there, you can actually gather this data that you are actually collecting. When the angle of incidence was 30, you get what the angle of refraction, you get the angle of refraction. When this one was 30, when this one was 30 degrees, then you measure using a protractor. Actually, one of the apparatus we should have included here for measuring the angle is a protractor. For measuring the angle. So, so you are going to measure the angle of incidence here and the angle of refraction, and then you record there. Similarly, also you change the angle of incidence to 40, then you record what you get as the angle of refraction. You change the angle of incidence to 50, then you record what the angle of refraction is going to be there. And using now a calculator, actually one of the apparatus you also require is actually a calculator. It's very important. You're going to have a calculator to help us actually get the sign. So you use a calculator to get the sign of incidence 30. What is the sine 30? You record there. And also what is sine R for the angle of refraction that you got, you record. And there also what is sine 40, you record. Also what will be the corresponding angle of refraction. Then also what is sine 50, you get there. And what will be the other angle which you found as the angle of refraction, you get there. And then you divide sine I, which will be the value you got here, divided by the value you got there for sine R. And this gives us actually the refractive index or index of refraction. So we are going to record the index of refraction there, a value, again there a value, again there a value. What it means, that's why I've written N1. It means that merely these values would be constant to be the same. It will be almost the same, because this ratio actually verifies Snell's law that it will be actually the same. So the lateral displacement here, since we are using almost the same material, but the different angle is also, you get some value there. You get some value also there. You get some value there. You get some value here. I've already indicated that the denser the material, actually the lateral displacement also actually increase. Let's see what that means. And then you can now plot a graph, which is a graph of sine I incidence against sine R. So you can put your sine I on the y-axis, and the sine r along the x-axis. This is y-axis, and this is the y-axis. So you get these values, and then you plot. When you plot, basically you get a straight line, and then you can find the gradient, okay, by looking at this point here, and 1, 2, 3, 4, and 1, 2, 3, 4, and this point there. So you're going to subtract this minus that to get the numerator. Similarly here, we're going to look at this point there, and that point there, and then you'll get the gradient. So the gradient actually is going to give you, as we indicated, so this would be sine I divided by sine R. So it gives you actually the index of refraction, or actually refractive index. So the gradient here gives us the index of refraction, which is also known as refractive index. Okay, and so this is what it means here. The gradient actually gives us the refractive index, or the index of refraction, the gradient of sine I against the sine R. And also the lateral displacement, as I indicated, it increases as the density of that medium increases, because the refraction will be towards actually the normal. And so we can now state the Snell's law, which this is the man actually who developed this concept. It's actually coming, this statement is coming from him, where he stated that actually the ratio of the sine of the angle of incidence to the sine of the angle of refraction is actually constant, as we have demonstrated there. It is going to be constant. And so what it means is that he said that if you have a index of refraction for a material 1, you multiply it with the sine angle of incidence, should be equal to refractive index for material 2 multiplied by sine of angle of refraction. This is what he actually demonstrated, this man known as Snell's law. So this is actually, any one here is the refractive index of the material. For example, if we have two materials here, maybe this is glass and this is air. What it means is that N1 would be the refractive index of air, and this is our normal. Then you get the angle here, which is the angle of incidence, and you get the angle there, which is the angle of refraction. According to him, this will be a constant value. According to actually Snell's law, it states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is always a constant value. This is what it means. And so the index of refraction, which is, I said, also is known as the refractive index, can also be actually gotten by looking at the speed. What it means that it is given by actually refractive index given by n, which is equal to the speed of light in a vacuum, meaning where there is no air, over the speed of light in the medium. So this is what it means here. So refractive index is actually C here, simply means which is equal to actually refractive index is equal to C over V. As we have indicated, C here is the speed actually of light in a vacuum, and V here is the speed of light in that particular medium. And the speed of actual light in air or in a vacuum, it is found to be 3 times 10 to the power 8 meters per second. This is why the one we've written here. It is actually found true. So if we know the refractive index and we also know the speed of actually light in a vacuum, we can be able to calculate the speed of light in that other material. That's what it means. And so this helped us actually to demonstrate that actually, according to Snell's law, the ratio or this sine of angle of incidence over the sine of angle of refraction is actually constant, as we saw in that graph. And so I thought today we can look at this lesson. For those of you who would want one-on-one lessons online, you can actually contact me on this number, +260 977 41 9949, or my email, small letters, all of them, KS Yamasaka at gmail.com. So we can go through actually these lessons in depth and actually rigorously look at the questions which come in exams. And so those who would want, again, we can tailor to actually the course you are doing. For example, if you are doing O-levels or you are doing GCE, all you need to do is to give me actually a course outline, or I can look for a course outline for that particular course you are doing, and then I can be able to actually give you appropriate lessons in depth. And so here we have merely looked at the concepts, but there are a lot of questions on Snell's law which we can actually practice. So I thought today we can look at merely the concepts for refraction of light. I thank you.